Welcome to Engineering Apex. We uncover the story behind the speed. Subscribe for the deep dive. The hypercar world operates on a singular currency, speed. Yet, as performance crept towards the 300 non-pi barrier, that conquest transformed from a simple mechanical hurdle into a defining philosophical conflict. This is the ultimate high-stakes battle between brute force and surgical efficiency. The core conflict is rooted in the cubic wall of air resistance. When we analyze the fundamental physics governing top speed, we see that the power required to overcome aerodynamic drag increases cubically with velocity. At the point where the speed needle ticks past 250 mph, this relationship becomes terrifyingly punitive. Bugatti met this challenge with the W16 quad-turbo platform, a testament to raw power, generating well over 1,500 horsepower. This engine's massive displacement and forced induction provide an overwhelming solution due to the cubic drag problem. The cost of this solution is significant mass and the colossal engineering required for thermal management. Conversely, Koenigsegg's V8 philosophy focuses on power, density, and radical mass reduction. Their engineering goal is to reduce the effective frontal area and achieve an ultra-low coefficient of drag. One is designed to punch a hole through the air, the other is engineered to slip through the seams. The difference dictates every subsequent manufacturing choice. Now let's open the factory blueprints and deconstruct the story of this engineering titan. The diametrically opposed design philosophies established in Act 1 necessitate two fundamentally different manufacturing hunts. When we move from the concept models to the factory floor, the differences manifest in the very structure and component sourcing of the vehicles. Bugatti's pursuit of brute force demands a chassis built to contain and control gargantuan forces, while Koenigsegg's obsession with low drag efficiency requires a precision structure defined by lightness. For the Bugatti W16 vehicles, the manufacturing focus revolves around load-bearing, capacity, and thermal management. The monocoque chassis, typically a carbon fiber composite, must be engineered to handle the immense torque, often in excess of 1,600 Newton meters. Factory footage reveals the complexity of the plumbing. Multiple radiators, intercoolers, and sophisticated oil cooling circuits are required to manage the colossal thermal byproduct of nearly 1,500 horsepower. This vast thermal sink dictates the car's overall architecture and contributes to its substantial curb weight. The complexity is compounded by the all-wheel drive system, which requires heavy-duty differentials and drive shafts manufactured with aerospace-grade steel alloys to manage stresses far beyond those of typical supercars. The manufacturing tolerances must be held tight, not primarily for lightness, but for absolute, uncompromising reliability under sustained maximum load. Koenigsegg, by contrast, executes a manufacturing hunt focused almost entirely on optimization and mass reduction. This is evident in their pioneering use of the Carbo-Titanium monocoque structure, a proprietary material compound where titanium wire is woven into the carbon fiber prepreg. Patent filings show this material provides enhanced strength and crash protection without the weight penalty of conventional reinforcements. The true manufacturing challenge is the seamless integration of their active aerodynamics. Unlike the Bugatti, Koenigsegg utilizes hydraulically controlled winglets and diffusers that constantly modulate the car's relationship with the airflow. These components are manufactured with micrometer precision actuators and ultra-lightweight composites. The focus shifts to specialized tooling and autoclaving processes to cure the complex carbon fiber shapes, ensuring a perfect, continuous surface that minimizes drag-inducing turbulence, a critical feature for maintaining laminar flow at extreme velocities. The manufacturing difference boils down to this: Bugatti hunts for components that can survive the assault of its own engine. Koenigsegg hunts for components that simply aren't there, achieving speed through the elimination of mass and the maximization of aerodynamic efficiency. The conquest of 300 mph was not merely a mechanical achievement. It was a defining moment in the hypercar lexicon. Yet, the data surrounding these top speed runs reveals the ultimate limits and the enduring technical legacies of both approaches. When we analyze these certified performance results, we encounter a critical piece of myth-busting: the difference between a one-direction maximum and the two-way average. Bugatti's record run, which established a peak velocity significantly past 300 mph, demonstrated the brute force W16's raw capability to overwhelm atmospheric resistance. The technical legacy of this platform is an affirmation of its original premise: a 1,500 horsepower plus engine, packaged for stability and luxury, can simply conquer physics through sheer power. It is a monument to controlled force. Koenigsegg, conversely, achieved its certified two-way average record by adhering to the more rigorous standard, proving that its success is rooted in the perfection of low drag, stability, and efficiency. The technical legacy here is one of material and aerodynamic mastery, demonstrating that reducing the power requirement through intelligent design is not only sustainable, but arguably more repeatable and fundamentally sound. However, both philosophies eventually confront the same absolute limit: the tyre-physics barrier. Regardless of how power is generated or how drag is minimized, the tires are the only connection between the car and the ground, and their ability to withstand the forces of centrifugal expansion. At 300 mph is the defining constraint. At this speed, a tire is undergoing immense rotational stress, threatening catastrophic failure. The manufacturing tolerances for these specialized tires are arguably the tightest constraint in the entire system, forcing the compound and internal structure to behave almost like a solid component. The conflict concludes in a profound lesson. While Bugatti proved the achievable limits of combustion engine power, Koenigsegg established a parallel and perhaps more enduring legacy of efficiency, proving that sophisticated material science can bypass the need for sheer mechanical excess, charting a more agile and optimized path for the future of speed. The story of the 300 mph barrier is a mesmerizing chapter of human engineering, defined by the courage to face impossible physics. Whether driven by the mighty bellow of the W16 or the sharp, surgical precision of the low-drag chassis, these machines stand as profound evidence of what happens when ambition meets uncompromising technical execution. It is a reminder that the true apex of engineering is not just in solving the problem, but in dictating the terms of the fight itself.